what we're doing in our sim lab this week is we're going to look at heat exchangers. So identify a few and how they work and how they're set up. So we have a few a little bit of work theory we have to cover off on heat exchangers. And actually, it's a pretty heavy chapter, to be honest, in your textbooks. So I sent you guys the kind of the section. It's early in the book, so unit 3, I think, unit 2, something like that. So anyway, so we talk about a few things. One, heat transfer modes, and I think I'll try to move through as quick as I can through that section. And then we'll talk about heat exchangers and different types and what their function is. So, so we all know what a heat exchanger does, right? It exchanges heat, right? That's what a heat exchanger does. So, so let's talk about how heat can move from place to place. So first of all, our second law of thermodynamics comes into play. And I don't know if you've talked about the laws of thermodynamics, but the first law is accounting for heat. So we can't create or destroy heat. Or energy, we only have a fixed amount, and heat is a form of energy. Our second law of thermodynamics sets some rules around how heat and energy moves. And generally, it moves from a state of high energy to low. And when we talk about heat and temperature, heat goes from hot to cold. And that's the normal pathway for heat. We have 3 different common ways that heat is moved. So we have conduction, convection, and radiation. And we can have combinations of all of these types of heat transfer. So conduction, convection, and radiation all happening at the same time, or maybe only 1 or 2. But we can have a bunch of different ways that heat is transferred if we want to move heat. And it always moves in the direction hot to cold unless we help it with some other energy. But the natural movement of hot to cold. Okay, so we have conduction, and we can think about conduction being the movement of heat from different atoms or molecules that are in contact with each other. And the hotter something is, the more it tends to vibrate and have small little movements. And if that object comes in contact with something else, it'll transfer some of its movement to the next object. So we start out with a high energy hot object touching a cold object, and it's going to transfer some of its natural movement or energy. And the cold one is going to get warmer, and the warm one will get, or the hot one will get a little cooler. And eventually, over time, everything should balance out so that we have shared energy and everything gets to the same level of energy or movement. And that energy or movement is equivalent to the temperature of the object. And so that's kind of the pathway for conduction. It's movement of energy from atoms that are in contact with each other. And generally, we consider that conduction happens within solids. So we, have this measurement of conductivity, which is how well energy moves through the solid. But it can happen through any type of substance. So, but in general, the more dense the material is, the better it is at conducting. Those atoms are right in close contact with each other. And so our solids are generally our densest objects. So things that are good conductors have a high conductivity value, copper, aluminum, for instance, and things that have low conductivity, so I don't know, concrete, wood, for instance, don't transfer very much heat through conductivity. So if we were to have a heat exchanger and we wanted to promote exchanges of heat, Generally, they're going to be made out of metals, and we try to maximize our conductivity. I don't know. Maybe I don't know if I'm going to. Yeah, sure. This is kind of the major equation for conductivity. Okay, and we have a few things that go into how much heat can be transferred. So Q is my rate of heat transfer, or amount of heat, I guess, in the way I've drawn up my equation. And so what comes into play is how conductive is the material? How much area do I have where heat can move? What is my temperature difference? And what resists conductivity is then how much of a distance does that heat have to move, or in other words, the material thickness. And so all of these things come into play when we talk about heat transfer with conductivity. Let's just keep moving here. Okay. We have generally, when we talk about heat exchange in a boiler or heat exchangers or other things, we have fluids that are moving around. And when we have fluids that are moving around, we have another form of heat exchange that's pretty important to us, which is convection. Okay, and convection requires something to be able to move and flow. So typically a gas or a liquid. And as it moves, it passes a surface, and it's going to be able to either remove heat or gain heat from the surface. The faster it moves past the surface, or the more surface that it passes by, the more heat it's going to be able to exchange. Okay, and we have two different ways that we classify convection. One is what's known as natural convection. Okay, and here's how natural convection works. So when something gets heated up that can flow, it tends to become more buoyant. So the density drops and it is able to rise. So hot air rises. So if we had air that filled this system with a hot surface, the hottest air is going to be next to the surface, and when it gets heated, it's going to tend to rise. When it rises, it has to push out any air that was in this area, and it's going to have to push down to fill the void. And so we have cold air that keeps circulating in to fill the void that's created by the hot air rising. And so we have this circulation, this convection current that gets created, which continuously circulates hot air rising and then the colder air coming in to fill its space. And this would continue until this whole area, I guess, is heated up to the same temperature of that surface. So natural convection doesn't rely on anything other than just natural buoyancy and movement of fluid in order to move heat around from place to place. Natural convection can't work if we have a hot surface that's at the top, because then we don't have the natural movement because of buoyancy and other issues. Okay, so hot surface has to be down at the bottom in order for natural convection to work. We have another form of convection that can work in any orientation, which is known as forced convection. So instead of us just relying on buoyancy to move the fluid, we force it. And this could be a fan blowing air over a hot surface. It could be a pump moving water through a heat exchanger. Yeah, it could be anything where we are forcing that fluid to move, not just relying on it to move with natural buoyancy and convection currents. Because the forced convection case generally has fluids that move faster than a natural convection, it tends to have a much higher rate of heat exchange. So us pushing that fluid through allows more exchange of heat because there's much more movement of the fluid, and it does a much better job of either moving heat in or out of a system. The other thing that forced convection, I guess, could work is in the absence of gravity. So if we were up in space, we'd have to rely on forced convection as opposed to natural convection. I have a couple of heat exchangers here. Okay. So this one we may typically see inside of a house that is used to exchange heat. This one happens to be called a radiator, but in general, a lot of the heat transfer that comes out of this is by convection. It doesn't have a fan, and hot air collects at it. So this thing is down low in the space, and the hot air is going to rise. And then in the rest of the room, we get colder air that comes in and fills the space, gets heated, and keeps moving. So this thing creates a natural movement of warm air and cold air through the space, continuously heating and cooling that space, and should maintain a reasonable temperature. Okay, so this guy works on natural convection, is one of the ways that this thing heats and moves heat. This one, in comparison, is set up with a fan. So in behind we have a heat exchanger, and we have a fan to push it. And the reason why we have a fan is, one, this guy is mounted up on the ceiling. Okay, so we have this heat exchanger that's on the ceiling. So we know that natural convection isn't going to work if our heat source is up high. And if we want this heat to move around to a larger area than just what's being set up with our natural convection, we can use the fan to force a much larger area that heat is making its way to. The other thing with the forced convection, because it generally can absorb much more heat or exchange much more heat, we can get away with a smaller heat exchanger to be able to exchange the same amount of heat if we have that fan pushing air through. Okay, so this guy kind of benefits from the flow of air. We can position it anywhere we want. It can be a little bit smaller because it has better heat exchange. It's can kind of heat a larger area than this guy can. Okay, we have one final form of heat exchange, radiation. Okay, and radiation is like light is a form of radiation. Okay, and so what we have is a means where energy can move from surface to surface through electromagnetic waves. And so, as I said, light is a common one where the sun transmits heat to the earth. But we have all kinds of different waveforms that get transferred using radiation. Everything that is hotter than absolute zero is going to emit some form of radiation from the surface. And the hotter things are, the more radiation gets emitted from any of those surfaces. Radiation doesn't have to move through any medium. So convection has to have a fluid moving around. Conduction, we need to have molecules or atoms in contact with each other. But radiation doesn't require a medium for energy to be transferred. So it can go through space, and we see that with the sun supplying heat to the earth through space. There's always a back and forth exchange with radiation. So every object emits radiation, and the hotter it is, the more radiation it sends out. So when we have a hot and a cold surface, both are emitting radiation, but because the hotter surface has a net larger discharge of radiation, we have heat going as a net from the hot to the cold surface. So we have kind of a transfer both from hot to cold and cold to hot when we're talking about radiation, but the net heat exchange happens hot to cold. So radiation kind of plays by a little different rules than the conduction and convection, but the net effect is the same when we talk about radiation. Heat's always going to move from the hottest to the coldest surfaces. If we talk about the equation for radiation, so when we talk about the amount of heat that's radiated from a surface, we have an equation that looks like this, and really what we have is a few factors that come into the heat exchange rate. We have the emissivity, so how good is a surface at emitting radiation. We have kind of a physical constant, so that always is the same value in the equation. And then the things that change are going to be your area, so how much surface area is able to emit radiation. And then what is the temperature? And the temperature is to the 4th power. So that's where radiation really, really rockets. So when you have something that's very hot, like the surface of the sun, not only is it exchanging lots of heat, but it also does so with temperature to the 4th power. So with that to the 4th power, hot surfaces emit a significant amount of radiation. And the hotter that we have, the more radiation is sent out. So this thing amplifies itself very, very quickly. And things that are, let's consider to be very hot, quickly radiation becomes the major form of heat exchange. When we absorb, or when radiation hits a surface, it can do 3 things. It can either reflect. Okay, so if we have a mirror or something like that, it's going to reflect light. So that could be one thing that radiation does. If we have a window, it's going to be able to transmit some of the light. So we can have light passing through it, just like any other form of radiation. Or else, if it doesn't reflect or it doesn't transmit, it can be absorbed. And so that surface can start to heat up. So that's 3 things that happen if we have radiation. We have 2 cars on a sunny day, and one of them probably is going to be hotter than the other. And typically what we might think is the black car might get hotter than the white car. And reasoning for that is, well, the black tends to be a color that can absorb more radiation. So this guy has a little higher absorptivity than this guy. And what that means is he's better at absorbing some of that radiation that comes from the sun, and it drives the temperature up higher. Keep on blasting through. Sorry, it was a quick little blast to kind of introduce our 3 types of heat exchange so that we have a bit more time to talk about our heat exchanger types. Okay. So we have our, let's call it 4 types of heat exchange. So we have conduction, which we can think of as moving heat through a metal as one of the primary things we do with a heat exchanger. We have convection, forced and natural movement of heat in or out of a fluid that's in contact with a surface. And then we have radiation, which is moving from surface to surface, moving heat from that. And especially with very hot surfaces, do we have radiation. Okay, when we have heat exchangers, we have the need to exchange heat from generally fluid fluid to fluid inside of a power plant. Okay. Sometimes we have cases where we have to air cool something, and we may have air that's cooling a surface. But if we talk about heat exchangers where we have typically fluids that we're moving heat from one place to the other, that's going to be the majority of what we would consider to be heat exchangers. And when we talk about heat exchangers, we have a couple of major classifications. So the first one is we may describe a heat exchanger as being either an open or a closed heat exchanger. And then we also can classify different heat exchangers by the way that fluids flow through them. And we have a couple of major classifications: parallel flow, counterflow, crossflow, and then combined cross-counterflow. And we're going to just talk about what do those classifications and those types mean for a little bit. So without looking at any of the specifics of types of heat exchangers, let's understand what those classifications mean. Okay, so here's the difference between an open and a closed heat exchanger. So an open heat exchanger, what we might have is two flows that come in. So we have a hot and a cold, and inside of the heat exchanger, they mix together and combine and create one flow that, should be a combination of the cold and the hot. So some warm flow that comes out. But there's no separation from the two flows. So whatever I put in, the cold and the hot, all gets combined, and I'm left with one larger flow that comes out. Okay. And so if we don't have any sort of separation between those flows, or they're able to mix together, we consider that to be called an open heat exchanger. An example of that might be like a faucet on your sink. Okay, we mix together a hot and a cold flow, and we can adjust the amount of hot and cold water going in, and all of it gets combined at the end in order to produce warm water for me coming out. Okay, so that would be I guess a good example of an open heat exchanger. The other one that we have would be more typical for an industrial process would be a closed heat exchanger. Okay, and a closed heat exchanger is one where we don't mix the fluids. So they're always separated from each other. And so a closed heat exchanger, the very basic one that we might have would be, we have two flows and we have a small little metal separation in between them. The hotter fluid's going to move, the colder fluid's going to move, and because heat's going to move from hot to cold, it's going to move into the colder fluid. But a closed heat exchanger, we don't have any mixing, so we always are separated with the fluids. And these are actually pretty important because we can have two different fluids, right? This one, if we're mixing water, we have to mix with water in order to get water coming out. Maybe over here I've got oil and I've got water on this side. So we could have two different substances that are moving heat from the other, or maybe we have the same substance, but we just don't want them to mix at the end. So closed heat exchanger, there's no mixing. Open heat exchanger, there is mixing. Okay. Okay. We also have some ways that we can organize our heat exchangers, and these would be for closed type heat exchangers where we don't have any mixing of the flow, so they stay separate from each other. So my flow type number one is what we would consider to be parallel flow. Okay, so in my drawing, I have my heat exchanger here, and yes, my flows are parallel, and parallel probably isn't really a good good word, but the flows are going in the same direction. Okay, so a a closed heat exchanger operating in parallel flow will have flows going in the same direction. And so one thing that we see when we have a parallel flow heat exchanger, when we have our entry point, we have the largest temperature differential. Okay, so we have, say, 90 degrees coming in here and 10 degrees coming in here. Well, heat exchange is based on a few things. We got surface area, we have the types of fluids that we have. But one of the major ones when we're talking about fluid to fluid movement is how much difference of temperature do you have? So in this case, I have 90 and 10, so I guess I have 80 degrees of difference. So I'm going to have a large heat exchange rate at the very start of my parallel flow heat exchanger. Well, the large movement of heat from my hot to my cold is going to tend to cool down my hot fluid, and it's going to warm up my cold fluid. And as it does that, the difference in temperature gets smaller and smaller. So parallel flow heat exchangers have a large amount of heat exchange that happens at the very start, and then they get worse and worse the further that you go through the heat exchanger as those fluids get closer and closer in temperature. Okay, so parallel flow, they do a good job right away, and then they kind of get worse and worse the larger the heat exchanger is. One thing that we can't do with a parallel flow that we'll see in a counterflow is we're limited by the temperatures that can leave that heat exchanger. We can never get colder than the lowest cold temperature. Okay, sorry, if our job is to cool down this hot fluid, it can never get colder than this point, and we'll see that in a second. But in this case, we started at 90, and maybe the best we could do would be 55 degrees leaving this heat exchanger. If we compare that to a counterflow, so a counterflow heat exchanger is, I guess, a better way to describe than the parallel before. I think that counterflow is a little easier for us to envision what's happening. This case, we have flows that go in opposite directions through that heat exchanger. So I'm going to start out with the same temperatures, 90 degrees that enters my heat exchanger on the hot side, and 10 degrees that leaves on the cold side, or sorry, 10 degrees that comes in on the cold side. So my 90-degree water, if I'm trying to cool it down, is always going to be in contact with some cold water, okay? But it's already been warmed as it's made its way through that process. So we can see here that my cooling water has made its way up to 70 degrees, whereas I think before it was somewhere around 45 or so. And I tend to maintain about the same temperature difference as I go through this heat exchanger. And why that's important is that the temperature difference dictates the heat exchange rate. So this heat exchanger has a much more even rate of heat exchange through the entire heat exchanger. And also, because I am heating up or using cooling, like if I'm trying to cool my hot fluid, I'm doing so with my warmest water, I can get away with a much more, like a greater amount of heat exchange through this system. The hot can get colder, and we see it's, in this case, it's down to 30 degrees, whereas before it was stuck at 55 degrees. My cooling water, if I was wanting to warm this up, can get up to a higher temperature, so 70 degrees, whereas I was maxed out here at 45. The other thing that's important about parallel versus counterflow is that if we talk about how these things actually interact with each other, and how I don't know the right word, stresses that are on this, because this guy has sudden changes in temperature. Okay, so my temperature is changing very quickly as it moves through and then evens out. This type of heat exchanger configuration tends to have a little more, be a little bit more stressed. It sees a lot larger temperature differences, and that can lead to this heat exchanger being, a little more under more stress, so thermal stress. This heat exchanger, because it's always a lot more consistent with its temperatures, is set up a lot better in terms of stresses inside of that piece of equipment. So we have a couple of benefits to a counterflow. One, we do a better job of heat transfer, so we can exchange more heat, and it's a lot better balanced. Right? And so for those reasons, you'll tend to find that counterflow heat exchangers are the most common type of heat exchangers that you'll see. Okay, so that arrangement. Parallel flow are good in cases where we need to exchange heat as fast as possible, as much, and we don't really care about the outlet conditions. But if we need a heat exchanger to do a good job and be transferring the maximum amount of heat, counterflow is what we want. Okay, so let's take a look. We won't go to the poll everywhere. I don't think we have time to do that. But we got this drawing here, and we have a furnace. So we have a gas furnace. And I'm wondering, is this furnace a parallel flow or is it a counterflow? I'm wondering if you guys can see and try to figure that out.
So I think it's a parallel because the air is mixed with this, and I think it's a parallel. It's open.
It's not, I don't think so. It's open because if it's an open, then the heat would go different. So they take his radiation from the heat, and then so the air would come flow, gets warmed up by the furnace, and supply it to the rest of the house. So I think it's a it's a
Yeah, so this is a closed heat exchanger. So that was the term. So let me just draw out what it looks like here. I don't know if that can work. Maybe not. Maybe not. I don't know if it'll let me with the.
it's a counter. It's a counter.
All right. So air comes in. Okay, and I have two sides to this. I have an air side.
Yes.
Okay, and the air passes through with the fan, the blower here, and then that air makes its way up to the house to supply hot air to the living space. Okay, I also have a second pathway here, which is, oops. Sorry, I'm trying to change my pen. I'll do it in blue. So what I have is the heat exchanger side, and I have my heat source. So my heat source is going to be these gas burners, and they're going to supply heat through my heat exchanger. Okay, and then eventually whatever's left over will go outside. So I don't mix the combustion products with the air I'm breathing in the house. So it's going to be a closed heat exchanger. The gas side where it has its flame, and the return is going to be one isolated system, and then the airflow through the blower to the supply is going to be a second pathway. So I have a closed heat exchanger, and then the question is this a parallel or is it a counterflow arrangement?
It's parallel.
They both go. Sorry, go ahead.
So it's parallel.
Yeah, I agree that it's parallel, and here's where I can look, right? If I
Because both they go
out,
the same direction.
great.
Yeah. Yes.
Everything's going the same direction. It's all going up through this.
Parallel, yeah.
Okay, so and I could look at it right here, right? My red line's going up, my blue line's going up, so they're going in the same direction where they leave. This one is I think a parallel system. So the flows are going in the same direction as they move through. Typically your furnaces actually aren't set up that way. They're probably set up the other way in a counterflow, because we can get a little more efficiency out of the exchange. This one's good for a quick and fast exchange, but typically your furnace now would probably be set up in the opposite direction, counterflow. Okay. Couple other types of heat exchangers. So we have what would be deemed to be a crossflow. Okay, and so these aren't really parallel or counterflow. We have flows that cross each other at a 90-degree angle. Okay, so a car radiator may be an example like that. We have a surface area and air can just flow through it, and there isn't really too much of a difference between where it comes in or out. We have a continuous flow in two different ways, and generally it's 90 degrees difference between the flow paths. So we call that a cross flow. And that typically would be if we have like cooling water or something like that, and we need air to pass through it, we often use a cross flow arrangement. Okay, so cross flow heat exchanger. And then sometimes what we have are heat exchangers where we have kind of a pathway where it keeps kind of looping. So you have, maybe a cross flow here, and then we had another sort of like, a few layers of these, and we call that, as it becomes a little more complicated than just fluid moving through 90 degrees with multiple passes, we call that a combined cross counterflow heat exchanger. So we have I guess a couple different arrangements, but your main ones are going to be really understanding parallel flow and counterflow, and then our last one would be like a cross flow, and those would be your top three. Okay. Going to just talk a little bit about different configurations of heat exchangers, so some things that you may see. So the very basic one, most basic heat exchanger would be what we consider to be a bare pipe heat exchanger. And a bare pipe is just a tube, and it moves through back and forth to kind of add some heat exchange surface. And that can be used to heat a different fluid, be it air that maybe is moving over, or if it's submersed in water. So we could use it to move heat from one place to another. Bare pipe heat exchangers aren't all that efficient and effective, but one thing that they are is easy to clean and cheap. So you have the very basic setup, but yes, often in a place where it's going to be easiest to clean is the key thing with this type of heat exchanger. And we would use the term when it's dirty. We use the term fouled. So I don't know if you guys have heard that term before or not, but fouling of a heat exchanger means we've lost the ability to exchange as much heat because the surface is dirty. So that affects the amount of heat transfer that can happen. Okay, so our bare tube is our most basic type of heat exchanger. How we can make a bare tube exchange more heat is what's known as a finned tube. So in a fin tube, what we do is we take that bare tube, which has the fluid that we're trying to heat or cool moving through it, and we add a whole bunch more surface area. So the surface area that we add is on those fins, and it allows a lot more surface for us to move heat in or out. And this fin tube is generally made with metal, or the fins, which allow energy to be conducted directly down into the tube. So we kind of absorb heat onto the fins, and then that energy is able to move through the fins through conduction, and then makes its way into the fluid that moves through. These guys have significantly more heat exchange potential than a bare tube, but we have a couple of disadvantages to them. One, it's more expensive. Okay. Two, it is a lot more likely to get fouled, so a lot more surface area and a lot more space where if we have dust or something like that is going to get stuck in those fins.
And so the fin are open access to the pipe, so there is any liquid that would go inside the fins, or the fin they just radiate the heat.
Yeah, so they are just absorbing heat out of the tube. So the tube itself would just generally be like that would be where the fluid would be moving through. Yeah. And then these fins go over on top. And I have a picture of just how that's done and just on the next slide as one typical way. The other thing is that compared to this guy, it's a lot easier for us to blow air across. So if we had a forced convection and a fan that was blowing air across this type of tube, it doesn't take much effort to blow air. These guys, because we have such small passages, it does take a little bit more fan power to blow air through these types of tubes. And typically we wouldn't be able to rely on natural convection for this. We'd have to force air through. So anyway, more fan power with that guy. Here's how we may go about making a fin tube. So we have a tube, and then we have a bunch of fins, and these guys might be just like made out of aluminum or some sort of metal. And we may have them like they're round. Okay, they're going to be round. Like if we look at kind of this profile, they're round, and then they have a little kind of leg that sticks out like this. So one way that we may create this fin tube is we take the tube and then we kind of push it through a mandrel, which we might use to expand the tube, and then that makes the tube a little bit larger, so it pushes up and has a nice connection to that fin. So that could be one way that fin tubes are made. We expand the tube to fit the fin. Otherwise, we may have it that we have a continuous sort of wrapping of a a strip around that tube that then gets like either welded or bonded to the tube surface. But either way, what we want to make sure is that we have very good tight connection between the fin and the tube so that we maximize our heat transfer rate between those things. Okay. So we may go one step further than that, and we may go to creating a heat exchanger that has several kind of tubes, several passes, and we add in fins across all of those tubes. So this one has a significant amount of fins and a significant amount of tubes and is able to do quite a bit of heat exchange compared to just a single tube or a bare tube type design. But
it just look like a radiator or a fridge. You know, sometimes a fridge radiator have it in the back, and they have a fan to force the.
Yes, so generally you're going to need to push air through this. So either by, if it's in a car, that the car is driving and there's air that can flow through, or it has an auxiliary fan to push air through. But we can't rely on natural convection to allow air to move through this because it just gets clogged. But you see these types of heat exchangers in all kinds of applications. And generally in this case, moving heat from a liquid to a gas, generally air, would be the prime application of this type of heat exchanger. Okay, and this guy we could consider to be, just as we go back to our terminology, probably one of those cross counterflow arrangements, right? So air moves across the heat exchange surface at 90 degrees, and we've got some section where we have air that comes in, and then it makes a bend and goes back in, or sorry, water coming in, and then comes back in to return back in the opposite direction. So this guy would be a cross counterflow arrangement. Okay, so those ones we would use if we're exchanging to air. Let's talk about some that we would use if we're trying to exchange water to water. So, and these could be run with air and other things, but these guys would be typically what we'd see if we're exchanging water to water. So we need a place where we can contain the water in order for it to flow across some of these tubes. And so this is one that we would call a shell and tube heat exchanger. And realistically, these things look and kind of perform similarly to like
water tube boiler.
Yeah, exactly. So it looks kind of like a boiler, right? So we've got different designs of boilers, and these boilers are just heat exchangers, right? They're just heat exchangers where we have a phase change that happens. So these guys share a lot of sort of the design ideas with boilers and other components. Okay, so what we have would be a U-tube heat exchanger. Okay, and so these guys are typically inside of a shell, all right, some sort of like casing that can generally hold some pressure. And then what we want to do is move fluid through them through a series of tubes. Okay, now these guys generally don't have fin tubes inside. They're all going to be, for the most part, bare tubes. But what we do is we would have a case where we have two different fluids. So we have a tube that comes in and supplies some fluid through this U-tube. And then we would also have a fluid on the shell side. So you have kind of your water moving through. And we could think of it this, if we go back to looking at it like a boiler, it's kind of like we have a water tube boiler with a fire tube boiler, right? We've got like water that goes through the tubes, and we've got water that goes through the outside. And instead of having a fired section, both of them may be just water moving through. And so we have a case where we have, you know, a heat exchanger, and it generally is going to do a good job with water and water.
Yeah.
We also may have baffles inside. Okay, so we want this water as it comes in to be able to be in contact a maximum amount with the tubes that it's trying to exchange heat to. So we may have baffles that direct the flow through. So essentially makes it more effective with the surface that we have, because we have a lot more passes across those surfaces. And it tends to do a better job of making sure that we have our hottest fluid in contact in the right spots, and we don't just lose the hottest or coldest fluid moving through our heat exchanger. It has to go through a pathway and follow the correct path. Okay, so these guys are pretty like rugged and industrial. So you could picture this as having some, pipes coming into it, and if it gets knocked, it's not going to get damaged. And so we see these in a lot of industrial applications where we would use them. So shell and tube type heat exchangers. About baffles a little bit, and keep going here. So here's a picture of one. And one thing that I just want to note is that, like you can undo the caps generally at the end of these heat exchangers. And if we undo the caps at the end of the heat exchangers, then we can access inside to clean. So these things have the ability to be able to be cleaned and maintained. So we're able to kind of take these things apart, and if there's any fouling or contamination inside, we can access that and we can clean them. So they're pretty functional for industrial applications, and they may get huge. So depending on the configuration of these, you've got some significant size to these. Couple things when we talk about just the layout for these. We have a couple different ways that flow can move through a tube and a shell and tube heat exchanger. So I've only shown this really as one pass. So we have either a flow through the tube side from one end to the other, and on the shell side, we've got kind of a flow that moves through. So we want to be careful that we think about it in terms of having a parallel or a counterflow arrangement. So if we look at, for instance, I don't know, let's say our non-condensable water side, okay, we can see here by looking at the flow paths whether this is a parallel or a counterflow arrangement. And if we look at the direction that, say, my shell side would go, so cooling in to cooling out, it looks like it moves to the left, and water in to water out, it looks like it moves to the right. And that would generally be the preferred arrangement for this non-condensable or water if it's moving through, or any real way that we configure this heat exchanger would be in a counterflow arrangement. So this guy moving to the left, this guy moving to the right indicates to me a counterflow arrangement. Okay, we have a lot of let's say flexibility with how we arrange water, but if we're using something that's like condensable, like steam, so if we cool down steam, it will turn to water. We want to be careful with how we're arranging it within a shell and tube heat exchanger. So the steam generally is going to have to come in from the top, which means any water that's formed will collect at the bottom and be able to make its way out of the shell and tube heat exchanger. So if we're trying to turn steam into water, we do have to be careful that steam is going to have to come in from the top and water is going to have to leave from the bottom. And
Is that same as the condense? What would be after the turbine, after the steam would go to the turbine and go get reheated, come back after finish with the turbine, loses energy, comes down to the condenser bowl.
Great, yeah. So at the end of the turbine, so we have steam that leaves the turbine, and the condenser is always going to be located below the turbine, and the reason for that is that the steam has to come into the top of the condenser. So once it turns into water, then we would collect that water after the condenser, and you would then have pumps at the very bottom underneath it to send it back to through your process. Yeah. So condensers always would have steam coming in the top, water leaving the bottom, and that would be essentially the application for this. A condenser is a very large shell and tube heat exchanger generally, but it's still usually the same style of heat exchanger.
But to cool it down, where's that water come from? Is it from something nearby, or it's also part of the process of the cooling system?
So in order for a power plant to work, a conventional steam-based power plant, you have to have a couple of heat, what we call reservoirs, okay? But basically what it means is we have to have a source of high temperature heat, and that's usually a fuel that we're burning, okay?
Yes.
But we also have to have a spot where we can remove heat. And so normally in a power plant where what's going to be the source of cooling water might be either, say in the case of like the nuclear power plants in Ontario, they draw in water from the Great Lakes. So cooling water from the Great Lakes would be their source of cooling, and that would be their cool reservoir. And other places may use air, so they may have giant heat exchangers to exchange air or heat to the air. Or else you have cooling towers would be another kind of spot where we exchange heat. So those would be probably your three most common. And I think in Ontario, probably just raw cooling water from lakes and rivers is pretty common. Okay.
Thank you.
You're welcome. Okay, so we just have a couple other types of heat exchangers just to talk about. If we go to a little less like industrial or a little less, I don't know, let's call it like a little like a step down from a shell and tube, we may have what we call a shell and coil heat exchanger. And basically what we have is the same thing. We have some sort of outer casing, and then inside what we'd have is just a coiled tube that runs through. And so it basically looks similar to a shell and tube, but what we don't have really is as complicated of a design inside. But the thing with these ones is that they're not really serviceable. So if this thing gets plugged up, we can't open it up to clean it out. We don't really have the ability to, replace tubes. We don't have the ability to clean this system out. They're basically, if they get wrecked, we throw them out and we replace it. So these guys are a little less functional, I guess, than a shell and tube type heat exchanger, but they're used in a lot of smaller type applications for sure. So you'll see these kind of shell and coil heat exchangers. And I'm just going to keep going. Okay, so one that's really common that we would see is what's known as a plate type heat exchanger. Okay, and a plate type heat exchanger, what it has is a number of these thin metal sheets, and on either side of the sheet, they kind of have like a pattern that's been pressed into them, and what they have is then a place where fluid can move through on sort of alternating sides of the plates. And so what we get are a bunch of these plates stacked up, and every time we alternate a plate, then it's like fluid A that passes through, fluid B that passes through, A, B, A, B, A, B, A, B, A, B. And so what we can see is that by stacking in a number of these thin plates, 50 of them or so, we've suddenly created many, many flow paths where heat can be exchanged. So plate type heat exchangers are pretty common in industry because they have a really, really high rate of heat transfer. And we can see what these look like. So here's a case like this, kind of metal, kind of corrugated, like with a little rubber gasket. And that's going to be one flow path that goes through this section. On the backside, you would have the opposite. So you'd have the other fluid that is allowed to move through on the opposite side. And we keep alternating AB, 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 so that we have essentially all kinds of different flow paths where those fluids can exchange heat from one place to the other. In order to keep them from leaking, we have to squeeze them together. And so what we typically have are a couple of big, stiff steel plates that are bolted together that sandwich in all of those little plates. And so we can get into this guy by unscrewing these and opening up the heat exchanger. And we can do a couple things. One, we can go in and clean it. So if it gets all fouled up, we can go and spray it out and clean up what's inside. The other thing that can be done with these is that you can expand the heating, the amount of heating it can do or cooling it can do by adding in more plates. So you can take away plates, or you can add plates depending on how much heating or cooling needs to happen inside of these heat exchangers. But typically they're very high heat transfer rate. But the risk that you face is that because there's a whole bunch of small little passages that you have to move through, they do have a higher risk, I guess, of getting clogged up if there is any contaminants that move through there. So if you have sand or something like that that moves through, it's going to get clogged, all of these passages pretty quickly. So you have to be careful with that type of heat exchanger. Okay, but you'd identify it by really these big steel plates on the end and leading to the heat exchange surface in the middle.
And I guess if you have any leakage with them, you might have to take them all out and change all the gaskets.
That can be the case. So they are fairly like they're reasonably low maintenance until you have the point where you do need to maintain them, and then it is quite a bit of work to reset them and reseal them and that. So yeah, you hope that you don't have any leaks, but it is a pretty big undertaking if you do have leaks with it. Okay, so let's just talk about some heat transfer mechanisms. So we talked about different types of heat exchangers and what they might look like. We talked about heat transfer styles. One of the things in your textbooks that they introduced to you is, let's talk about a boiler and let's talk about what type of heat transfer occurs and how exactly does it happen. Okay, so we have a conventional boiler. We're burning some sort of fuel. I think in this case it's probably coal that they're burning. But in any event, we're creating a high flame, so very hot flame somewhere in there, and we're trying to transfer it to water to create steam. Okay, so we have a couple of sections. So here's our boiler, and basically we're going to burn fuel down here, and then the hot air is going to move up and through our boiler and then would exit out over here. Okay. And on the water and steam side, we have water that comes in, goes through an economizer, makes its way up around here, and I guess over to probably our boiler steam drum over here. And it moves itself in and through kind of in the whole furnace area, and then would make its way, oh no, sorry, the other way around. So from the economizer, probably through all the furnace walls and everything, up to the drum, and then would go through a superheater over here and a couple different pathways to come out as high temperature superheated steam. So air or fuel burn here and move their way through, and water comes in through here, comes down, I guess, through kind of the furnace area, boils, and then the superheated steam, or the steam superheats through superheaters and other pathways at the top here. So first thing that we have is our furnace. Okay, and our furnace, what basically we have is a bunch of fuel that's burning, and it's going to be extremely high temperature. And so when we have extremely high temperatures, radiation is going to be our number one heat transfer mechanism. And so in here, basically what we would have is heat transfer by radiation from our furnace and the fuel that we're burning to the walls of this boiler. And those walls would be used to absorb heat in this case. Oops. And that would be our primary form of heat transfer in this section of the boiler. Okay, high temperature, generally going to be radiation is the number one pathway. The flame here is going to create radiation that's going to then absorb into the metal of the walls of the boiler. Okay, and in this case, if the radiation goes to just bare metal tubes, it would get so hot that it would start to melt some of these tubes. So in order to keep them cool, we have to keep water in these tubes, and the water does two things. One, it picks up the heat, which is great, but it also means that it can keep the metal cold enough so that it's structurally strong to support the pressures that the tubes are operating. So we get radiation that gets absorbed to the tubes, and in order for it to make its way to the other side, we have a couple of forms of heat transfer that happen. Radiation makes its way to the outer edge of that metal. Conduction takes the heat through the metal, and then convection transfers heat to the fluid that's passing over that surface. So we have all kinds of different heat transfer mechanisms when we talk about that energy making its way into the water or the steam inside the boiler. After we've gone through the boiler a bit, we get to the point where we've lost some of that heat. And once we've lost some of the heat, the temperature has gone down, and we're no longer at the point where radiation is going to be our primary heat transfer mechanism. Okay? And so we may be going through sections here where we have tubes that are either bare tubes or fin tubes for picking up heat, and the economizer might be an example of that. Same thing in our superheater sections. We have some superheater sections that are still in this very hot zone where they're picking up heat through radiation to the surfaces. And then we have some others that are further downstream where it's cooler, and then we're typically getting convection as the primary way that heat is being gained by those tubes. So air, as it passes over, heats up the tubes, which then transfers to the steam or the water that's inside. I'm going to keep going. Keep going. All right. Sorry, I'm going to just back up here. Okay. If we talk about heat exchange fluids, so we often say, okay, well, water or steam is our number one thing. But really any fluid can be used to exchange heat. So we have air, we have oils, we have like glycol or antifreeze, we have all kinds of fluids that we may use as heat exchange fluids. And if we think about why or what we might consider to be important in a heat exchange fluid. We have some things like how much heat can it either absorb or give off. So the thermal conductivity, the specific heat capacity. We may think about, is this thing at risk of either boiling or freezing, or do we want it to boil or freeze? So we may want to know what temperatures do those occur at. Is it toxic? Is it corrosive? What sort of cost does that fluid have? And all those things may come into play when we're thinking what would make a good heat exchange fluid. But in general, what we want is a fluid that's going to be able to absorb lots of heat if we want it to absorb heat, or if we don't want it to absorb heat, maybe we want it to be able to give up its heat pretty readily. So those would be some considerations.